Hello, everyone. Welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll, and we're continuing today with our series on ideas about quantum field theory. Quantum field theory counted as one big idea, but when we talked about it, we didn't get very far. Quantum field theory is a gigantic, extremely rich subject, but it's worth devoting a few videos to it because it's the best description of the universe, of reality at a deep level that we currently have. It might not be the final description, but it's a pretty good one so far. So we talked first about field theory in the sense that you take a field, you quantize it. We showed how in the simple case, where those fields were free, where they were non-interacting, it looks like a collection of particles. And then we did a video on interactions, Feynman diagrams, where we showed how to think of those systems of particles as interacting with each other, turning into other particles, and actually calculate the probability of that happening. That was good news. Everything was really, really good. And in fact, that procedure is what we use in particle physics to actually calculate things at the Large Hadron Collider and elsewhere. But there is a lurking problem there, so we have to go to today's topic, renormalization. Now, the idea of renormalization often gets glossed, defined as hiding the infinities. I'll mention that there are infinitely big quantities that show up when you do quantum field theory in a straightforward way. We have to get rid of them since the physical quantities we measure are not infinite. But that's kind of an old-fashioned way of thinking about what renormalization is. These days, we have a more modern perspective on it. The perspective is not actually that modern in that it comes from Ken Wilson in the 1970s and goes under the name of effective field theories, but it's taken a while for people to catch on that this is a better way of thinking about renormalization. So let me mention why you get renormalization in the first place. And the idea is that you get infinities from doing Feynman diagrams. Feynman diagrams were the calculational tool that we used to actually calculate the likelihood that if two particles come together, they will turn into different collections of particles. And we said that any one process is given by a sum of many Feynman diagrams. So very roughly, we have some process where two things come in, there's a blob, two things go out, for example. And we said, well, this is a sum of Feynman diagrams. Maybe here's a Feynman diagram. We're going to forget details about electrons and photons and all that stuff. We're just going to focus in on some simple scalar fields for this lecture. So you have maybe a diagram like that, and then you have more complicated diagrams with more vertices, more lines in them, and then there's an infinite number more, okay? And we said that these diagrams are not just pictures of processes, they're actually calculational tools. We use them to assign numbers that then add up to give you the amplitude for a certain kind of process. And the hope was that as the diagrams become more complicated, the numbers that you calculate using them become smaller. That's because every vertex in the diagram is associated with the square root of alpha in this case, and actually not in this case, in the electromagnetism case. So alpha is a small number, so the more powers of alpha, the smaller the overall contribution of the diagram becomes. Except that there's another subtlety that makes this second diagram that we've drawn infinitely big. So this number, this diagram that we drew has the feature that there are no loops inside of it, okay? We have a label for diagrams like that. These are called tree diagrams. It looks like the branches of a little tree coming out. This diagram, you can go in a loop around the internal legs of the diagram. There's a closed loop that you can describe, which doesn't exist in the first one. So we call these loop diagrams. And what happens is, tree diagrams are indeed finite, but loop diagrams can become infinite. And the reason has to do with the fact that these virtual particles that we draw on the inside of the diagram, they're not really particles, it's a story that we tell each other, and there's a certain amount of energy that is flowing through them, as we discussed. So for the tree diagram, for example, you might say, if you just draw this simple diagram like this, just try to expand it to follow the energy going through, you have E1, E2, E3, E4, and there's some energy that goes through, let's say, in this direction. You pick the direction up to you, that's a convention. And by that convention, we would call this, what are we going to call it? E bar is an energy. And then you know that E1 equals E3 plus E bar. And then you can go through E2 plus E bar equals, oops, that's a 4, E4. And then you get a specific answer. In both cases, you know exactly what E bar is, and together you figure out that energy better be conserved. E1 plus E2 equals E3 plus E4, and can we get that there? Yes. And E bar is given by either one of these equations, E1 minus E3 or E4 minus E2. Okay, but the point is there's no ambiguity, there's no freedom. E bar is a certain amount of energy that goes down the diagram. Once you know the momenta of the particles you started with, E1 and E2, the energies, and you know the energies of the particles that come out. By the way, I sometimes mix up the words energy and momentum because in relativity, as we discussed before, there's really not just a three-dimensional momentum, there's a four-dimensional momentum, and the energy is part of the momentum, and it's related to the spatial momentum by energy squared equals three-dimensional momentum squared plus the mass squared of the particle. So energy is not independent. So sometimes physicists use energy and momentum both to mean the same concept of what's going down the legs. Anyway, given the fact that both energy and momentum are conserved in this diagram, the value of E bar and the corresponding value of P bar, the momentum, are just fixed. There's nothing ambiguous about them. You know what they are. Try to do the same thing with the loop diagram, and you run into a little bit of trouble. So let's try to do this for a loop diagram. We'll draw, let's say, this box that we've been drawing for a loop diagram. Okay. Label things E1, E2, E3, E4, and we'll have the energies go this way, this way, this way, as before, down, right, 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 and then up, just to complete the loop there. And if you call this top one, see, when E1 splits into two different lines, neither one of these lines is anchored. Neither one of these lines escapes the diagram. Neither one of these lines gives you a momentum or an energy that you will measure. So in principle, you say, let's let E bar, some amount of energy, go down this leg. Then what goes down this leg is E1 minus E bar. Oops. Okay? And then that leg with E1 minus E bar joins up with E2. So this line here is E1 plus E2 minus E bar. Good. And then that sort of has E4 leaving before we go up at the final leg of the diagram. And this final leg, therefore, has E1 plus E2 minus E3 minus E bar. Good. And then the relationship we have is that this right leg of the box with E1 plus E2 minus E3 minus E bar joins up. Oops, it's not E3, is it? It's E4. Look, this is how charmingly informal we're being. That's just what you have to learn to live with. And then it joins up with E bar. So we get an equation, E1 plus E2 minus E4 minus E bar. Okay, that's what's going up in that leg right here. Right there, joins up with E bar, so we say plus E bar, and that combines to make E3. But you see what happens, two things happen. One is the E bars cancel. There's a minus E bar and a plus E bar, and then you just get E1 plus E2 equals E3 plus E4, if I move the E4 from the left to the right. So on the one hand, energy is conserved. E1 plus E2, the energy coming in, equals E3 plus E4, the energy going out. That's good. But on the other hand, the value of E bar is entirely undetermined by this. It can be anything. And remember, Feynman told us we have to add up the contributions of every single Feynman diagram. In this case, that means every single Feynman diagram with any value of the energy you get. So in fact, the Feynman rules say that the diagram that we drew this way, the diagram as a whole, has a contribution which is given by the sum over all values of E bar. This is the Greek letter sigma, meaning summation, of all the individual diagrams with some fixed value of E bar going that way. Now, really, the sum is over a continuous variable, E bar, right? So I could write this as the integral of this little box diagram d e bar, and that's the way that you'd actually do it, but we're not going to be quite that persnickety here. Just write it as a sum. The point is it includes all of the different values. Okay. Well, you can do that sum. This value e bar, remember, virtual particles, they don't obey this mass-energy relation right here that ordinary particles do. That energy can be anything, which means it can be any number from minus infinity to plus infinity. That's allowed for all of these things. And you add them up, and what you get is that this diagram equals an infinitely big contribution. That's the fact of what you get. So, and the reason why, just to emphasize it, is because E bar itself can go to be infinitely big. So that's the problem. That's the origin of the problem. The problem with Feynman diagrams is that once you get to loop diagrams, which are going to be most of the diagrams, right, they can be very complicated. They can come with a lot of factors of some small number, alpha, to some large power. But if you multiply that small number by infinity, you still get infinity, right? So these are the divergences of Feynman diagrams, the divergences of quantum field theory that have caused problems. And it was a difficult problem in the sort of 1940s, 50s. This is what people were struggling with. I should say that, maybe you could take the attitude that maybe this shouldn't bother us. Remember when we talked a little bit about the vacuum energy in quantum field theory. We talked about the fact that if you have a classical theory where the 0 point of energy, the lowest point of energy, where the field wasn't doing anything, where the kinetic energy and the gradient energy were all 0, then you did a quantization of that theory, then there's an extra quantum mechanical contribution. Every single mode of the field acts like a harmonic oscillator. Every harmonic oscillator has a 0 point energy over and above the classical value of 1/2 h bar omega. So there's an infinitely big energy density in empty space if you do the naive quantum field theory prescription. But the whole point of saying that was maybe you shouldn't have been so naive. Remember, that's just a calculation not of the value of the vacuum energy, but of the difference between the classical value and the quantum value. In the real world, there's no such thing as the classical value. The real world just is quantum mechanical from the start. So the real world doesn't know that you chose to start with some classical contribution and then add to it a quantum contribution. The real world just knows the answer. So in some sense, the same thing is true here. In a very real sense, because of these virtual particles, the loop diagrams are intrinsically quantum mechanical. You could do perturbation theory in classical field theory, and what you would do is only have tree diagrams. That's the way it works out. Anytime you have a loop diagram, the contribution is proportional to h bar, Planck's constant, to some power, and therefore the loop diagrams are intrinsically quantum mechanical. And the limit as h bar goes to 0, they go away. So maybe the philosophy you can take is, sure, these diagrams are infinitely big, but the thing that is infinite is just the difference between the classical prediction and the quantum prediction. The real world is just the quantum prediction. Maybe the classical prediction should be irrelevant. And that's fine. That's a perfectly good attitude to have. The problem is, how do you convert this into a useful calculational scheme, right? And so this was the task undertaken by Feynman, but also Schwinger, Tominaga, and also Freeman-Dyson was the one who showed how it all fit together. And they showed a way to renormalize quantum electrodynamics. Remember the theory we looked at with this electrons, positrons, and photons was quantum electrodynamics. And the way that they would have put it back when they were developing this formalism was they had a way to cancel the infinities. Really, they would often say, somewhat tongue-in-cheek, they were sweeping the infinities under the rug. And really, literally what they would do is say, okay, there's an infinite contribution here. Let's add some extra Feynman diagram just by hand, which is not integrating over everything. It's just intrinsically there, called a counter term. And this counter term would be equal to minus infinity. And you would add it to the Feynman diagram expansion and subtract it off. And by saying it that way, it sounds completely hokey. It sounds completely impossible. Infinity minus infinity can get you a finite number, but infinity minus infinity can get you any number you want. That's not just what these folks did. What they did was give you a very specific, rigorous mathematical procedure for taking the limit of both the regular Feynman diagrams and the counter terms in such a way that you get a fixed finite answer. And the answer is amazingly successful. QED is the most rigorously, precisely tested physical theory of all time. I forget how many decimal places it is now, but something like 12, 13 decimal places of accuracy. The predictions of the theory and the experimental results work out to be in agreement. So, on the one hand, it was successful as a theory. It works. You can fit the data. That's good. That's what you want to do. On the other hand, it was a little bit intuitively unsatisfying. It felt like there was something deep and important going on that was just being hidden rather than being confronted straightforwardly. So this was figured out, really, to most physicists' satisfaction in the 1970s by Ken Wilson, who was a less famous person than Feynman or Schwinger, etc. But what he did was really set the stage for all of the triumphs of quantum field theory in the 1970s and beyond. So this is in the 1970s. And what he did can be summed up in the phrase, he invented effective field theory. An effective field theory is sort of a philosophy in some way, but it's also a very rigorous set of rules that you can use. The basic idea behind effective field theory is it's analogous in some ways. Remember when Hugh Everett said, you have all these branches of the wave function, and you know what? That's okay. You can just deal with them. They can just be there. It doesn't really bother you. What Ken Wilson says is when you do these Feynman diagrams, the reason you get infinities is because you're including contributions from arbitrarily high energies. And remember, energy is basically equal to 1 over the wavelength of the mode you're looking at, okay? There might be 2 pi's in there, etc., but that's the basic idea. And so high energies means short distances. That's where your infinity is coming from. But high energies and short distances is exactly where, Wilson says, we don't know what we're doing, right? We don't know what quantum field theory is actually telling us at those short distances. If we know some things, like, okay, we have electrons. Let's say you have electrons and photons, and you're doing QED, right? You should be able to do that, to do QED, without knowing about the existence of protons and neutrons. Those are much heavier particles. If you just have slowly moving electrons, you shouldn't be bothered by the existence of protons and things like that. Feynman diagrams that include protons in them shouldn't be relevant to you. Likewise, if you think that space-time itself breaks down at the Planck scale, at the Planck length, very, very short distances, maybe it does, but you've included in your Feynman diagram infinity distances much, much shorter than the Planck scale. So why should that bother you when you know that those might not even be there? So Wilson's philosophy is admit that we don't understand things at very high energies. And the way that he quantifies that, physics, let's say, at energies, he says, you tell me the energy scale up to which you think you do understand physics, and I will put a cutoff at that energies, greater than some cutoff energy E star. So this is called the cutoff. Okay? And what he says is, we admit that, but it's not just we admit it, we put that into our equations explicitly and see what happens. And the goal is to use this fact that what matters to us are the physical predictions, not the way that we got them. So if we can make a scheme for inventing physical predictions that doesn't depend on what happens at energies above the cutoff, then that's what we should use. And that's exactly what we're able to do. So in pictures, what you should imagine is, here's energy. And Wilson says, we can divide all of the modes, right? We have all these wavelengths, and the wavelengths are related to energy. They're inversely proportional. So we have some cutoff, E star, and we label everything at energies above E star high energy, the ultraviolet, as it is called. And this is regimes where the wavelengths are short. Okay, so these are short wavelengths. And down here below the cutoff, we have long wavelengths. And this is the labels we put on here. This is the UV, okay? And this is the IR. And this is literally standing for ultraviolet, an infrared, ultraviolet short wavelength, infrared long wavelength, okay? And we say, look, the ultraviolet is unknown to us. We don't know what's going on there. The infrared is what we care about. That's what we're trying to invent a theory to describe. Now you might say, well, I would like to invent a theory that describes everything in the universe that goes up to all wavelengths. You know, bully for you. That is an awesome thing to try to do. That's what string theorists try to do, for example. So in that case, you would not be doing an effective field theory. You'd be doing a full theory of everything. But most of the time, when we do the standard model of particle physics or QED, when we do atoms and the Higgs boson and stuff like that, we're not pretending to describe everything in the universe. We're pretending to describe, we are describing things below a certain energy, below a certain cutoff. And then Wilson says it's okay to ignore what happens in the ultraviolet. In fact, it can be the case that a single infrared theory has more than one, or zero for that matter, ultraviolet completions, as we call them. So given the theory that we know below the cutoff, there may be many different versions of the theory above the cutoff that give us the same predictions in the infrared. So why are we sweating ourselves worrying about what's going on in the ultraviolet? Just to give you some numbers here, you know, we always set C equals to 1 when we do particle physics, C equals 1. So and E, the rest mass, we know is mc squared. So if C equals 1, then E equals m, and we often use energy and mass interchangeably. So just to give you an idea of what we mean when we say a cutoff, you know, the mass of the photon is 0. The mass of the electron, you know that, right? The photon is massless. The mass of the electron, it is typical in particle physics to describe masses of particles in energy units rather than in mass units, because we always set C equals 1. And the unit we typically use is the electron volt. I don't know why we use the electron volt, to be perfectly honest. The electron volt is the amount of energy it takes to take one electron and move it through an electrical potential of 1 volt. That's how it's defined. And it turns out the mass of the electron can be written as 0.511 million electron volts. MeV equals 10 to the 6th electron volts. Whereas the mass of the proton is, I think, 938, if I'm remembering correctly, MeV. So roughly 1 GeV, 1 billion electron volts. So 1,800 times bigger is the mass of the proton than the mass of the electron. And the Planck mass, right, this energy scale that is purportedly characteristic of quantum gravity, is roughly 10 to the, 27 electron volts. So that's 10 to the 18. I picked MeV, which is dumb because I usually think in terms of GeV. So let me just write, let's stick with it. 10 to the 21 MeV, okay? The point is, the Planck scale, these ultra-high energy scales, they're way bigger than the energy scales of particle physics or of, let's say, chemistry, right? If you say chemistry, e-chemistry, what do I mean by that? Well, if you have different chemical reactions going on in your body or in a test tube or something like that, what's really going on is the electrons in the orbitals around the atom are hopping into different energy levels or combining and so forth. So there is a characteristic scale, which is maybe between 1 and 10 electron volts. That is the reason why electron volts are convenient units. So all of these are way smaller than the masses of the particles that we're talking about. Anyway, the point is there are these large hierarchies in the energy scales of particle physics. So it is very plausible, at least, that you can imagine doing physics at a low energy scale while ignoring energies at a high energy scale. That's the philosophy of effective field theory. To be fair, you might have a little bit of anxiety about this because you might say there's various kinds of anxiety. We'll talk about them as we go along the way. Here is one. You say, look, if I have a physical system made of multiple moving parts, right? Let's say, I have a lot of springs that are tied to each other in different ways. Generally speaking, I cannot just say, well, I'm going to ignore some of the springs and I'm going to keep some of the other ones. I would not get a sensible, closed, internally consistent theory that way. So Wilson is not just saying, oh, let's ignore things we don't understand. He's saying that we can consistently ignore these things we don't understand and still get a consistent theory for the things that we're keeping track of. And roughly speaking, the reason why is because these ultraviolet degrees of freedom are not doing anything dynamically, okay? They might appear in the inside of quantum field theory calculations, of Feynman diagrams, but that's sort of a passive role. As long as none of these ultraviolet degrees of freedom, particles or new forces or whatever, are part of the ingoing particles or outgoing particles, whatever their effect is, it just gets mushed together in one big effect. That is literally renormalization. It gets renormalized into one big effect. Let me show you what that is in action, okay? To put this into action, what I'm going to try to argue is that this idea of ignoring ultraviolet degrees of freedom and focusing on infrared ones not only sounds good because it gets rid of infinities. Oh yeah, I didn't actually say this. Let me finish. Let me finish the whole point of this here. The point is, in the effective field theory, okay, in what Wilson says, ignore the ultraviolet theories. What that means, what that amounts to is, treat this kind of diagram as the sum over energies that are less than or equal to the cutoff. So E bar is less than or equal to E star, the cutoff of this diagram, where there's a specific value of energy E bar going around. And that will turn out to be finite. That's the scheme. That is the effective field theory approach. You can make all of your calculations finite by imposing an explicit cutoff. And there are a few reasons you might want to worry about that. So one is that it just doesn't give you a consistent theory, but I'll argue that it does. The other is that E star, the cutoff, okay, seems arbitrary. I will talk about that later. Meanwhile, let me just tell you why this works. Because it works very effectively, as it were. And the reason why it works comes down to dimensional analysis. Now, once again, I have to apologize because the word dimension is used in yet again a different sense than has been used before. We talked about dimensions of space, up, down, left, right, forward, backward. And I went to the pains to emphasize that that's a different notion of dimension than the simple abstract mathematical notion of the dimension of an arbitrary set in the mathematical sense. So Hilbert space, the set of all possible wave functions, is really big. It might be infinitely big. It might be just super big, but not infinite. But it has a large number of dimensions. And those dimensions are the number of independent vectors that you could add together, the number of perpendicular vectors you could construct in Hilbert space. Okay, those are not dimensions in the sense of a place you could go or a direction you could move in. They're different than the dimensions of space. This use of the word dimension is yet again a different notion of dimension. This is basically units, okay? If you took a introductory physics class in college, it's very possible, very likely, that the first lecture or two were on units in physics and dimensional analysis. So we attach units to different physical quantities, right? We talk about mass, energy, distance, time, stuff like that. In fact, the number of units is very large. Pressure has units, electrical resistivity has units, all of these things. But the key thing is, if you add two quantities together, they better have the same units. You cannot add a certain number of fluid ounces to a certain number of years. That makes no sense. You can multiply them together, but if you're adding different terms in an equation, all of them better have the same units. A nice feature is that you only need, for almost all purposes, you only need 3 basic units because you can combine different units together to form the set of anything you want. For example, energy, E, we know that there is a formula E equals mc squared, right? So this is a formula that says the energy of an object at rest comes with a certain amount of intrinsic energy, which is its mass, times the speed of light squared. And so if the units of both sides of this equation are going to add up, are going to be consistent, we better have the units of energy, which I'm going to write E in square brackets, better be equal to the units of mass times the units of velocity squared. Velocity is distance divided by time. So this is mass times distance squared divided by time squared. So all you need to express energy are units of mass, distance and time in whatever series you want. So CGS is a common choice. Centimeters, grams, and seconds. MKS, meters, kilograms, and seconds, is another common choice. But length, mass, and time, that's what you need to be able to measure. Now, particle physicists go even further. They say they're going to set not only C equals 1, but also H bar equals 1, okay? And the dimensions of C are, of course, it's a velocity, so it's distance divided by time. So when you set C equals 1, when you use units in which the speed of light equals 1, that automatically means that the units of distance are the same as the units of time. We can always convert distances into times and vice versa by multiplying by 1, by multiplying the appropriate factor of C, okay? So you see that by setting certain things equal to 1, different units become compatible because we've hidden a conversion factor, in this case, the speed of light. Likewise, we have H bar, its units, I don't know what its units are, but I wrote them down here, mass times distance squared divided by time. So now, if distance and time are the same, and h bar also equals 1, we can convert either distance or time into mass. And of course, mass has the same units of energy, and so forth. So we actually simplify our lives a great deal. These are called natural units, by particle physicists anyway. And as I said, I think, videos ago, they're so ingrained in my head, I don't even remember where the C's go and where the H bars go, but you can always work them out by dimensional analysis. There's another set of units, which is called Planck units, where you set C equals 1, H bar equals 1, and also Newton's constant of gravity equals to 1, and then all the units disappear. And I think that's going too far, to be honest, because keeping some units around is actually good for your soul and also good for checking your equations that you have not made mistakes. So we're not going to use Planck units. We're not going to set the speed. We're not going to set Newton's constant equal to 1. So the Planck mass, the Planck energy, these are all dimensionful quantities we will keep around. But we will use C equals 1 and H bar equals 1. And so in those units, given that all these things are true, okay, then it turns out we can pick one unit and just use that for everything. One unit to some power. And we're going to pick energy, because that's what particle physicists typically pick. Like I already told you, the mass of the electron in units of energy. So that's the kind of thing that we'll do. So in these units, what you find is that energy and mass have the same units. You knew that already from C equals 1. But also, distance has units of 1 over energy. You can work that out. And time, well, time has the same units of distance since C equals 1, so time also has the units of 1 over energy. Leaving a little bit of steps here for you to do at home because, it's kind of like you got to learn these things. It's fun to play around and do dimensional analysis. Look, let me tell you, for the next few minutes of the video, we're going to be kind of persnickety. We're going to be kind of careful and go through this. And it might seem like, why are we suddenly doing all this work rather than just leaping to the answer like we usually do? It will pay off, okay? We're going to do a little bit of dimensional analysis. It will actually pay off in a really interesting way. So stick with me. Why are we doing this? Why are we doing this dimensional analysis stuff? Well, we're doing field theory, right? And for simplicity, we're doing scalar field theory. And we want to be able to think about the equations of motion for our scalar field using dimensional analysis will help us understand what kinds of equations of motion we should expect. That's a remarkable fact. I mean, dimensional analysis is almost trivial, right? I mean, there's no substance in there. There's no statement that we've made about the nature of reality by doing dimensional analysis. It's just a requirement of mathematical consistency. But by doing it correctly, we will actually learn something, or at least it will suggest something about the structure of the equations that govern physical reality. That's an impressive feat. So in this scalar field theory, the first question we ask is, what are the dimensions of phi, right? What are the dimensions of our field itself? Our field will appear in the equations of motion for itself, so we would like to know what units it has, what dimensions. And we can't just guess. You don't invent a field theory you do invent a field theory. That's what physicists do all the time. They invent field theories, but you don't say, I'm going to invent a theory of a field with the following units. The units have to come out consistently from the equations that the field obeys. So what you do is you write down a field theory, you find its equations, and from that you derive what the dimensions of phi have to be. So for example, the example we'll use here is something that I'm just going to assert is true is that I know what the kinetic energy of the scalar field is. It's 1/2 times the phi dot squared. Phi dot is the time derivative, d phi dt. And really, if I'm honest with you, it's not the kinetic energy, it's the kinetic energy density. So the kinetic energy density, the reason why it's a density reflects the fact that in a field theory, the field exists at every point in space, right? Everywhere in space, there's a value of the field. It might be changing up and down. And so at every point in space, there's a little bit of kinetic energy. To get the amount of kinetic energy in a region, you integrate over that entire region, right? Every little point contributes to it. You add those up to get the kinetic energy. So the formula you originally propose is for the density, for the kinetic energy at any one point, the quantity you would integrate up to get the whole kinetic energy. And so that has units of kinetic energy, per spatial volume, right? It's a certain amount of energy in a spatial region. And the units of that, the equation for that is that it is 1/2 the derivative of phi with respect to time squared, okay? Sorry, my t's look a little bit like epsilons. That would be a mistake. So at every point, the field is moving up and down. It has a time derivative. It might be 0, but it has a value of the time derivative. And that value squared is the kinetic energy. That value squared times 1/2 is the kinetic energy. And this, I'm just telling you this. I'm not deriving it. I'm not justifying it. But it shouldn't be that weird or unusual looking. For a particle, the kinetic energy is 1/2 mv squared. And if you think of m as a constant associated with the particle, the kinetic energy goes like the velocity squared, the rate of change of position squared. So the fact that the kinetic energy of a scalar field goes as the rate of change of the field squared should come as no surprise. So let's do some dimensional analysis to this equation. Kinetic energy density, kinetic energy per spatial volume. The units of that are energy per spatial volume, which is distance cubed, right? Little tiny volume, 3-dimensional, distance cubed. We're assuming space is 3-dimensional for the purposes of this lecture. And we said that distance itself has units of 1 over energy. So energy over distance cubed has units of energy to the 4th. Good. And 1/2 d phi dt squared, rate of change of phi with respect to time, that has units. 1/2 has no units at all. 1/2 is a natural dimensionless number, okay? It's the same in any units. It wouldn't change if you went from centimeters to inches. A half is a half. Phi has units, so I don't know what those units are, but whatever the units of phi are, d phi dt squared comes with units of phi squared divided by units of time squared. So the d's don't matter. This is saying there's a certain change in phi per change in time, so the units of whatever that change is phi divided by time, and we've squared it. And we know that time has units of 1 over energy. We said that right up here. So this has units of phi squared times energy squared. And the units here better be the same, so we have energy to the 4th is the same as the units of phi times energy squared, so that works out if and only if the units of phi are energy. There you go. We calculated something in quantum field theory in some very ill-defined sense. Very loosely defined sense, not ill-defined sense, okay? The units of our field itself are that of energy. Now, by the way, that's true for this particular scalar field. For other theories, the units will be different. It turns out that in QED, for example, we have the electron, the positron, the photon. Electrons and positrons have units of energy to the 3/2 power. And the photons have units of energy, just like the scalar field does. So you have to keep your wits about you. You have to do this separately for every kind of field that you're looking at. Okay. Now, that was a little tedious. We had to do it. It's about to all come together in an interesting piece of physics. So remember, we had the action, right, when we define our theories. we have an action, and we're going to minimize the action classically. Quantum mechanically, we will do a path integral over all the possible paths and add up different contributions depending on what their actions are. None of that is relevant right now. What matters is the equations of motion for our field will be derived from an action. So the action we know is the integral of the Lagrangian over time. Good. And we know that the Lagrange density, the Lagrangian L equals an integral over the Lagrange density d3x. So this is the Lagrange density. And d3x, of course, is a little volume of space. An infinitesimally tiny volume of space, dx, dy, dz. So the point of this, I think I mentioned this before, but the point of this is in field theory, we're going to define our fields, our equations of motion for our fields, by specifying the Lagrange density. That is the quantity of interest. This is what particle physicists, field theorists spend all their time doing, is writing down Lagrange densities. So much so that they will often forget the word density. And even though the actual Lagrangian is the integral of Lagrange density over all space, they will refer to this quantity, script L, as the Lagrangian. So sometimes I will slip and do that as well. None of that is really important, but I'm focusing in on the Lagrange density because it is the thing out of which we will make our field theory, so we want to do our dimensional analysis on it. Well, what do we know? The dimensions of the Lagrangian, you know what those are, because the dimensions of the Lagrangian itself, for point particles, was kinetic energy minus potential energy. For field theory, it's the same kind of thing. At least there's extra terms in there for gradient energy and interaction energy, but it still has the same units. So the unit of the Lagrangian is just the units of energy. That's what the definition of a Lagrangian is, okay? And the units of d3x, well, that's a little volume of space, so it has units of size, distance, cubed, which is 1 over energy cubed, okay? So capital L, Roman L, has units of energy. d3x has units of energy to the -3. We can therefore infer that script L, the Lagrange density, better have units of energy to the 4th. This is what the Lagrange density needs to have for units to make everything work out. Then energy to the 4th times energy to the -3 equals energy. That all makes sense. Why? Why do we care about this? Well, remember, Professor Feynman taught us that there is a way of going from terms in the Lagrange density to Feynman diagrams, or in particular to the fundamental vertices, the basic interactions out of which we construct more elaborate Feynman diagrams. And roughly speaking, very roughly speaking, sorry about that, it goes like this. If you have a term that looks like phi cubed in the Lagrange density, then you will get a fundamental vertex, an interaction with 3 factors of phi. There's a phi, phi, phi. That's what a phi cubed interaction does in the Lagrange density. It corresponds to a Feynman diagram with 3 phi's. And remember, it doesn't matter whether 1 goes in and 2 come out, or 2 go in and 1 go out. We can move the lines as long as we keep track of particles versus antiparticles. If you have phi 4 in L, what I mean by this is the Lagrange density is a sum of different terms, right? Kinetic energy, potential energy, interaction energies. So when I say phi cubed in L, I mean when there is a term in that sum that is of the form phi cubed times some numbers, okay, times some coupling constants. Well, then you can guess what you're going to get. You're going to get a 4-point vertex, as it's called, 4 phi particles interacting with each other. Phi to the 5th in the Lagrange density implies that there is a vertex where 5 phi particles are interacting, and so forth. Okay. Now, wait a minute. This is telling us something, because remember that the dimensions of phi are the dimensions of energy. And we want the Lagrange density to have dimensions of energy to the 4th. So you might guess, and you'd be incorrect, but you might guess that you could only have phi to the fourth in your Lagrange density, because phi to the fourth automatically has the right units, the right dimensions, to be in the Lagrange density. It's energy to the fourth. Phi is energy, and phi to the fourth is energy to the fourth. That's what we want for our Lagrange density. But what we're neglecting in that is that each one of these possibilities also comes with a coupling constant. And so the solution to have any one of these, or more, right, etc., is to have the coupling constants themselves have the appropriate units. So what we do is we write L, and I'm not going to write out the whole thing. The Lagrange density for typical quantum field theory has a bunch of terms. We don't need to care about them. We're just illustrating some features of the general principle. So let's just write that there is some coefficient C3 times phi cubed plus C4 times phi to the fourth plus C5 times phi to the fifth plus etc. And you might say, well, okay, first off, I don't want to have all those terms. Like, what if I have a simple theory? What if my theory is just so elegant it only takes 2 terms to write down? Well, again, good for you, but we're doing effective field theory, okay? So even if you only had, this is a digression, I'm going to erase it. Let's imagine you only had phi cubed, C3 phi cubed in your field theory. That would lead to a Feynman diagram that is just this little vertex, okay? Phi, phi, phi. But then I could construct from that the following diagram with 4 lines in it, okay? And so that contributes to this blob where 4 particles are coming out. I could also construct a Feynman diagram that looks like this, where this contributes to a process where 2 particles go in and 3 go out, as if there was a fundamental phi to the fourth vertex and phi cubed vertex. And because the philosophy of effective field theory is that I neglect things at very, very high energies, I can't tell at low energies whether my phi to the fourth interaction or phi to the fifth interaction was fundamental, or whether it just came from integrating out, from including all the high energy processes that I'm neglecting above the cutoff. So for the effective field theorist, you don't have a choice. When you start writing down terms in your Lagrangian, you have to include them all. As long as they don't violate some symmetry or something like that, every term that you're allowed to write down, you have to write down. Because you're sort of hiding a whole bunch of effects, and therefore you have a mess at the end of the day. Now that doesn't sound like progress, right? That sounds bad. By neglecting things at high energies, we've forced ourselves to include a whole bunch of terms in our effective Lagrangian. Why is that supposed to be good? Well, because of this fact that we want the Lagrangian, Lagrange density, to have units of energy to the fourth, we know that these different coupling constants need to have different units. The dimensions of c cubed better be the dimensions of energy. The dimensions of c to the fourth, well, it's dimensionless, so we just write 1. This is a true number. Remember we did the fine structure constant. That's just a number. The fine structure constant doesn't have dimensions. 1 over 137. It's just a number. And that was okay because it was multiplying in the interaction Lagrangian electron, positron, photon. Electron has units of energy of 3/4. Energy of 3/2. Let me do this carefully. I can slow down. We're not in a hurry, right? For QED, we had an interaction Lagrange that looked like square root of alpha, E minus, E plus, gamma. Electron, positron, photon. It turns out that the units of the electron are energy to the 3/2. Units of the positron better be the same because they're antiparticles, right? Energy to the 3/2. Units of the photon are energy to the power 1, and therefore Lagrange density naturally has units of energy to the fourth, even though alpha is dimensionless. So that's nice. It's a nice little Lagrange density for QED. Good for us. But now we're doing this scalar field theory, constructing it from scratch. And so the coefficient of phi to the fourth, like alpha, is just a natural number. It has no dimensions. But C5 has units, and the units are 1 over energy, and etc. C to the 6th would be 1 over energy squared. C to the 7th would be 1 over energy to the 3rd, etc. Okay? So you can see the pattern. As you get to larger and larger powers of phi in your interaction Lagrangian, you get coupling constants that are larger and larger negative powers of the energy. That's just a fact. It's very natural. It's going to make dimensional analysis work out. Why do we care? Well, because there's a natural expectation. And here's where we begin to sort of wave our hands a little bit, but it's a good way of hand waving. The natural expectation is the following. Whatever the coupling constants of your theory are, these coupling constants are of an effective field theory, right? We have a cutoff, E star. So there's a bunch of things going up at above energies above E star, okay? So they all contribute to these effective parameters that we will measure, C3, C4, C5. And therefore, if we know what the dimensions of C3, C4, C5 are, we have a natural expectation for what their values are going to be, namely the appropriate powers of E star, of the cutoff. We would guess, if we didn't know any better, if there wasn't any fine-tuning or secretly tweaking the numbers behind the scenes, we would guess that C3 would be of order, this curly O means roughly of the order of, the value of the cutoff, E star. I mean, maybe it's 10 times bigger or 10 times smaller or even 100 or whatever, but it's not like if it were 10 to the 20 times bigger, that would be weird. That would just make no sense to us. We would suspect something was going on. C4, dimensionless, we would expect it to be of order 1. Remember alpha, which was the 1 over 137. So the parameter that appeared in the Lagrange density was the square root of alpha. So that is, in fact, of order 1, very roughly. It's not like 10 to the minus 20. C to the 5, we would expect to be of order 1 over E star, etc. As you go to higher and higher powers, more and more E stars in the denominator. And remember, we are working at energies well below the cutoff. That's the point. We're trying to construct a theory of processes and particles with energies well below our energy cutoff in the Wilsonian sense. And therefore, when you get to things like this, they shouldn't matter. Processes that have coupling constants that are of order 1 over the cutoff should be, technically speaking, irrelevant. So in fact, we invent some nomenclature, some language for this. We say, there can be, we didn't write it down yet, but there can be a term in Lagrangian C2 phi squared, right? We didn't write it down because it's not an interaction. It's part of the mass of the particle. The field squared is part of the free field theory that defines the mass of the particle. It's not an interaction with anything else. But we can put it in. C2 phi squared, C3 phi cubed. These are called relevant interactions. Whereas C4 phi to the 4th is called a marginal interaction, and C5 phi to the 5, C6 phi to the 6th, etc. are called irrelevant interactions. What we mean is, in the limit, as the cutoff gets very, very big, the physical processes that are governed by the irrelevant interactions literally become irrelevant. They become less and less likely. Remember, when we're talking about chemistry energies, right? 10 electron volts. And if you put a cutoff even at the Higgs mass, okay? The Higgs mass, remember, the Higgs mass was of order 10 to the 2 GeV, billion electron volts. Sometimes we talk about the Electroweak scale as sort of just a catch-all term for things that happen in this Electroweak theory. The Electroweak theory was this theory from Steven Weinberg in the 1960s. He unified electromagnetism and the weak nuclear force by putting in a Higgs boson. This is 1967, and then decades later in 2012 we discovered the Higgs boson. So we might say that roughly speaking this is like 10 to the 3 GeV. Okay, so that rough energy scale, 100 or 1,000 billion electron volts, is where modern particle accelerators have gotten up to. Okay, that's the Large Hadron Collider energy, roughly speaking. The highest possible thing you can get at the Large Hadron Collider is of order 10 to the 4 GeV or something like that. But the point is, all of these energies are well above what you do with electrons and protons in everyday interactions. So if you have a cutoff at, let's say, 10 to the 3 GeV, okay? If you're doing an experiment at 10 electron volts, and your cutoff, E star, is 10 to the 3 GeV. A GeV is 10 to the 9 electron volts, so that's 10 to the 12 electron volts. Then you can neglect terms in your equations of motion that are of order 10 divided by 10 to the 12 to some power n. Okay? That's 10 to the minus 11 times some power n. So all of these irrelevant operators are exactly that. They are contributions from your equations of motion, but they are suppressed by a big number 10 to the minus 11 outside them, or 10 to the minus 22, or 10 to the minus 33, or whatever. So that's why these are irrelevant operators. Now, in the old days, before Wilson came along, we spent a lot of worrying about what are called renormalizable theories. In other words, theories that in principle make sense all the way up to infinite energy by this trick that Feynman and his friends figured out by subtracting off the infinities. So renormalizable theories are those that only have relevant and marginal operators. I shouldn't say operators. Operators is the technical term. That's what people say, but let me say interactions, because that's what I said before. Okay, so here we go. Phi squared, phi cubed, phi to the fourth are either marginal or irrelevant. Phi to the fifth, phi to the sixth are irrelevant operators. And the point is that the trick that Feynman and Schwinger and Tomonaga and Dyson, the set of tricks that they figured out, work only if you start with just relevant operators and marginal operators. So if you started in your theory with irrelevant operators, then you wouldn't know what happens if you try to do physics at very high energy scales. Then these operators that were irrelevant at low energies would become super relevant at high energies, okay? And so you couldn't sweep the infinities under the rug. The infinities would really, really matter if these irrelevant operators were part and parcel of your fundamental description of the theory. If they're just in your effective theory with a cutoff, that's okay. That doesn't matter. But if they're in your fundamental theory, that would bother you. So in the 50s, 60s, even into the 70s, people thought that their job was to find theories that would work up to arbitrarily high energies. So it was a big discovery by Gerard de Tufte in the early 1970s that Weinberg's electroweak theory was renormalizable, that you could write it in a form where all of the interactions had this nice marginal or relevant form. Sadly, Einstein's theory of general relativity, if you try to quantize it as a quantum field theory, is not a renormalizable theory. But that doesn't mean you can't do quantum gravity. It just means you can't extend quantum gravity up to arbitrarily high energies. Einstein's general relativity has a quantum version as an effective field theory that works perfectly well. If you want to figure out the scattering of two gravitons at low energy, we can do that, no problem. We just can't extend what we're doing up to arbitrarily high energies. It's not a renormalizable theory in that sense. And these days, since we know that getting the theory of everything is going to be hard, it doesn't bother us so much if we write down a non-renormalizable theory. We only expect it to work up to a certain cutoff, unless you're actually trying to do string theory or the theory of everything or whatever. So those were the old days. These days, new days, we're happy with effective field theories. And the effective field theories have all the terms, have all the interactions, but the higher order ones, the irrelevant ones, are just very irrelevant. They're just small. Okay. So now the payoff comes. This was not yet the payoff. I tried to explain why we did this dimensional analysis to figure out that different interactions would naturally be relevant or irrelevant. But the payoff is that there aren't that many relevant interactions. Okay? There's only a small number. of relevant or marginal interactions you can write down. So what that means is, because basically, I mean, that it should be clear why that's true, because marginal or relevant interactions have a small number of fields appearing in them. Once you add more and more fields to make things more complicated, chances are you're making your interaction less and less irrelevant, something that drops out at high energies. So that's why effective field theories are so powerful, because even though we're admitting that we don't know what happens at super high energies, if you just tell me the fields that you have and the symmetries they obey, I can figure out what the effective field theory will be at low energies really simply. And it comes with a small number of parameters that I can then go measure, and I can use it, okay? So you don't need to know arbitrarily complicated things to do effective field theory. That is an extraordinarily powerful idea. You can try to go up to the cutoff and learn new things. There's a whole field of endeavor called electroweak precision measurements, which says the following thing. If you have interactions, if you have loop diagrams, okay, which loops are important and there's some energy floating around them, and you can look at energies for your ingoing and outgoing particles that are near the cutoff, then there's always a lot more experimental numbers you can measure than there are parameters in your effective field theory. Okay, the parameters in your effective field theory, C1, C2, etc., the relevant and marginal operators, it's a small number of them. That's the payoff. But there's a large number of things you could measure. You can measure decay rates and scattering amplitudes of different particles at different energies and so forth. So they're incredibly over-constrained. What this means is the good news, bad news situation. The good news is you can, in principle, discover new physics without discovering new particles. You can find a breakdown of effective field theory with the cutoff. You can find out that the prediction you make just on the basis of your particles and your effective field theory doesn't match with your experimental data. And what you would conclude is that your cutoff has gone up to the place where new physics is kicking in, where there's some particles or forces which you didn't know about, which maybe you're seeing the hints of. Even though they're only virtual particles, you can figure out that they're there. That's the good news, that the effective field theory can let you discover new physics even without directly seeing the particles. The bad news is that if your new physics is very, very energetic, is up there at mass scales or energy scales that are very, very high, then you will never see it. Then there is no experiment you can do that will show it to you because you just don't have the precision to reach those effects at those very, very high energies. This is why it is essentially impossible to test string theory at the Large Hadron Collider, right? The energy scale for string theory is roughly the Planck scale, so that's 10 to the 18 GeV. And the energy scale for the Large Hadron Collider is roughly 10 to the 3 GeV. Maybe 10 to the 4. Let's give it the Large Hadron Collider a little bit benefit of the doubt here, okay? But the point is, still 14 orders of magnitude away. And so every string theory effect that you might want to see is suppressed by 10 to the 4 over 10 to the 18 to some power, which is a tiny, tiny number. You might get lucky, as we said before, that you have a scaling with energy of a certain kind, but then there's a constant of proportionality outside. Maybe there's a stringy effect which, even though it's suppressed by this large energy factor, is still gihumongous by its own right, and therefore it has a tiny little effect, even at Large Hadron Collider energies. That's why it's important to try to look, but you shouldn't be surprised if at the end of the day you do all the experiments you can and you see no effects of Planck scale physics at the Large Hadron Collider or anywhere else. So that's the good news and bad news. Good news is you can do all this physics without knowing the ultraviolet. Bad news is you can do all this physics without knowing the ultraviolet, without learning anything about what's going on in the ultraviolet, without learning anything about what's going on at very, very small scales. Okay. Two more little facts I want to give you. One is not really a fact. I want to sort of assuage a worry that you probably had from the start. There's a worry with all this effective field theory stuff. Isn't the cutoff, E star, isn't the energy cutoff arbitrary after all, right? I mean, if I think, well, I understand physics up to 2000 GeV, but you think you understand physics up to 3000 GeV, then wouldn't we use different values of the cutoff in our calculations? And so aren't we including different Feynman diagrams, right? My Feynman diagrams are integrated up to 2000 GeV, yours are integrated up to 3000 GeV. Wouldn't that give us different answers, right? Well, no. So this is, again, the beauty of effective field theory is that the way that Wilson sets it up, you use the cutoff, this is your cutoff, energy cutoff. You use the cutoff to do your calculations, but none of the calculations at the end of the day depend on the cutoff. The parameters, what you would call the coupling constants, depend on the cutoff, but the physical answer for the probability that certain particles scatter or decay or whatever never depends on the cutoff. And this is called the renormalization group. And it's a terrible name because it's not a group in the group theory sense at all. But this is the fact that coupling constants, I'm going to put constants in quotes here, scare quotes. Coupling constants evolve with changing cutoff or changing energy. So what we do is we say that, you have some, what is the best way to say this? When I write my Lagrangian, my interaction Lagrangian, it includes things like C3 phi cubed, but that C3, the specific numerical value, will depend on the value that I choose for the cutoff. And then likewise C4, etc. And there's some very specific functional form for exactly that dependence. And we can calculate what that functional form is. So if you change your cutoff, you're basically saying that I'm including different kinds of energies than you are, and my coupling constants in my effective field theory shift to compensate so that the probability of any physical process remains the same. That's the renormalization group flow, as it's called, the flow of the coupling constants. All right. And that's not just a mathematical trick, okay? It's a real... Why can't I write the word flow? What's wrong with this? Look, it's late in the day, folks, where I'm doing this, okay? There you go. It's not just a mathematical trick. It reflects a real physical phenomenon. And so let me give you a cartoonish version of what this physical phenomenon is, something that you may have seen before, but let me give it to you. And you're more sophisticated now than you were a few lectures ago, right? A few videos ago. Here's an electron. An electron, as we know, is not a fundamental particle. It is a vibration, an excitation mode in a quantum field, the electron field. And also, as we know, there are these other fields, right? Positrons, photons, and so forth, that interact with the electron field. And we can think about them, courtesy of Richard Feynman, in terms of virtual particles popping in and out of existence, okay? And that's true not just when the particle is interacting in a Feynman diagram, it's true when the particle is just sitting there. You can think of this in this Feynman diagram language, which, remember, is just a story that we tell each other that helps us do calculations and get some intuition. The reality is there's an electron and there are fields around it that adjust to be in their minimum energy configuration, given that there is an electron there, okay? But the Feynman diagram language is that there are virtual particles popping in and out of existence. That makes you seem to get the impression that something dynamical is happening, and if you look at the electron over time, it will be changing. But it's not. It's an electron, okay? Nevertheless, it's very helpful to use this fun Feynman diagram language, so we'll do that. So we can think of this electron as being surrounded by a cloud of, let's say this is a positron, and this is an, positron. Here, let me show my technological abilities here by changing the width of my pen. Look at that. So here's an E plus, E minus. And we can imagine that our electron is surrounded by this cloud of virtual particle-antiparticle pairs popping in and out of existence, okay? All the time. This is the story that we're telling each other, even though it's not completely accurate. But still, these electrons, you have to be careful to sort of conserve energy. So if the energy of one is positive, the energy of the other is negative, etc., these virtual particles can interact with the electron, with the physical real electron, just like other things do. So there are photons that are exchanged between these. And guess what? And a negatively charged electron will attract positrons, which have a positive charge, and will repel other electrons. So there is an overall tendency for the positrons to be close to the electron. The positrons sort of align themselves up on the side closer to the electron, whereas the electrons, the virtual electrons, end up being pushed a little bit away from the real electron. And this is a real physical effect. This is called vacuum polarization. Polarization in the sense that there's a directionality to what is going on. And this physical effect has experimental consequences. Let me make my pen big again. The experimental consequences are the following. We probe the electron using other quantum fields. That's the only way we have of probing it. So when I say probe it, I say, we scatter a particle off it to measure the fine structure constant, for example. The fine structure constant is an encapsulation of the electric charge of the electron. The fine structure constant is a way of saying how powerful is the fundamental unit of electric charge. But when we measure the charge of the electron, we do it with some other quantum field, which itself has a wavelength, right? Because they're all waves. And if it's a low energy quantum field, then the wavelength is going to be larger. And that's like using a lower resolution probe. A large wavelength field doesn't probe as deeply close to the real electron as a high frequency, high energy probe would. So let's imagine that we have a low energy probe. Maybe what it can see around the electron is a region like this big. Okay, I'm going to draw a dashed circle to indicate what is actually being observed by some low energy probe, as opposed to a higher energy probe gets to sort of sneak inside and look closer to the electron because it has a smaller wavelength. So this might be the resolution scale of a higher energy probe. And what you see is, when you ask, using these different probes, what is the charge of the electron? The high energy probe, in this very simple cartoon that we've drawn, sees more or less the fundamental electron by itself. The low energy probe sees the electron, but also its effect, the effect that it measures, is also affected by these virtual particles. And the virtual particles are predominantly positrons, not electrons. It's not a 5-to-1 ratio like it looks like from this picture, because the electron-positron virtual particles are popping in and out of existence very, very quickly in this story. But there is a tiny shift in the effective charge of the electron, because the charge that the low energy probe sees is a combination of the charge of the real electron plus the vacuum polarization of these virtual pairs. It picks up some of the compensating charge from the positrons. So this effect, it gives the net answer that there is shielding of the electric charge. And the relationship of this to what we've been talking about with cutoffs and so forth is that if you think of these probes as being at your cutoff scale, the effective value of the electric charge is different with the cutoff. If you are sensitive to things at very high energies, the effective charge of the electron is larger because it's not shielded as it would be at low energies. And you can convert this into, literally you can plot the effective value of the fine structure constant, 1/137, as a function of the energy at which you probe it. And the fine structure constant goes up as the energy goes up. So it's not really a constant at all. At higher energies, the fine structure constant is more than 137, 1/137. And this is true for all of the different constants of nature. Well, what's true is that they change with energy scale. Some of them go down. The strong interactions have a feature that they get weaker as energies go up, and that will be important later on. So And this is observed in experiments, this plot. You can find this in the Particle Data Book, which is a famous book that collects all the different examples of particle physics experiments in the most modern form. So all this business about cutoffs and effective theories up to some scale and the renormalization group is not just because we're weak and we're not able to do things all the way up to the ultimate high energy scales. There's a physical effect going on here. When you really probe quantum fields, you're really probing them at some scale, and the scale at which you're probing them matters. That's where renormalization becomes very, very physical. That's a nice little good news picture. So now I have some bad news. And, look, it's not really bad news. In some sense, there's never truly ultimately bad news in physics. The bad news is because we human beings have trouble figuring out what the physical world is doing. But the world is doing something, okay? There's not bad news in the sense that physics doesn't make sense. Again, no one ever promised us a rose garden. It might be hard to figure out what's happening in physics, but there are clues given to us by exactly those things that we don't understand. So when I say bad news, what I mean is right now there's something we don't understand. Maybe that is a clue to something that is beyond our understanding, which we'll figure out and then call as very good news. And the mystery is, the thing we don't understand right now is the Higgs mass. Okay? I don't know if this was... You could have noticed this along the way to what we were already talking about. I gave you enough tools to figure this out, what is going on. The Higgs boson, which we discovered in 2012, is a quantum field, a scalar field, exactly like what we were talking about here. As I mentioned, it has a mass. There's a mass term in the Lagrangian for the Higgs field, 1/2 mass of the Higgs squared, h squared, where h is the Higgs field itself, okay? So we think that when we do experiments with the Higgs boson, like the Large Hadron Collider, we're not pretending to understand physics at super high energy scales. We're using an effective field theory with a cutoff. But we think the cutoff is a little bit higher, that we measured the Higgs boson mass to be about 125 GeV, billion electron volts. We think the cutoff should be a little bit bigger than that. And by the dimensional analysis that we did, we would expect, let's say that we had trust in the standard model of particle physics well beyond where we've experimentally tested it, okay? Let's imagine there's no new physics beyond the standard model until we hit quantum gravity or grand unification or something like that. In that case, we would say that I could imagine doing low energy physics with a cutoff up at the Planck scale. I don't need to put it at the Electroweak scale if there's no new physics. Okay, so we're going to have two choices. One choice is there's no new physics, and then I should be able to put my cutoff way up at the Planck scale. And then, in that case, we would expect the mass of the Higgs to be pushed up to the cutoff. And that should be of order the Planck scale. And that should be of order 10 to the 18 GeV. If there were no new physics above the Electroweak scale where the Higgs is, above the Higgs scale, we should expect the mass of the Higgs to be large. It's a relevant operator. That was our natural expectation. The whole point of the effective field theory spiel is that we have natural expectations for the values of these coupling constants. But it's not, right? 10 to the 18 is about 16 orders of magnitude bigger than the actual Higgs mass that we measure. This is called the hierarchy problem. There's a big hierarchy between the mass of the Higgs, or the Electroweak scale more generally, because the mass of the W boson and the Z boson, which are also part of Electroweak theory, are also of order 10 to the 2 GeV. So there's a huge hierarchy between the Electroweak scale and the Planck scale. If the Electroweak theory is an effective field theory and nothing else happens up to the Planck scale, we should expect all those masses to be up the Planck scale, and they're not, okay? So the other option is there is new physics. That would make us happy. If there is new physics to explain why the mass of the Higgs is so much lighter than the Planck mass or whatever, then that would imply that we should be able to see it by doing experiments at energies of order 10 to the 2 GeV. So we turned on the Large Hadron Collider in 2009, and we didn't see any new physics other than the Higgs boson itself at these energies. Supersymmetry is a famous example of a set of new particles that could have been found at the Large Hadron Collider and would very naturally have explained why the mass of the Higgs was kept low, even if we put our cutoff up to very high values. Basically, there were cancellations in the Feynman diagrams, so the mass of the Higgs did not get big. But we didn't see supersymmetry. It was not the only version of that theory. You can have large extra dimensions and other kinds of theories, technicolor theories. There's a bunch of options for what new physics at the electroweak scale could have been to help explain why the mass of the Higgs is small, to help explain the hierarchy problem. But at least so far, in the last decade or so of doing experiments at the LHC, we have not seen any of them. Now, it's always possible that they've conspired to just hide behind us. I mean, the LHC, as wonderful as it is not a super high energy machine. It's not as high energy as the superconducting super collider that we wanted to build here in the United States would have been if we had built that. So maybe, when the LHC turns on again, it'll be slightly higher energy and we'll see particles that we didn't see before. But the reality is it would have been very easy to already have seen particles at the LHC that would help explain the hierarchy problem, and we haven't seen them. So option one was there's no new physics up to the Planck scale, and then in that case, the natural expectation of effective field theory is the mass of the Higgs should be the Planck scale. That's not right. Second option was there is new physics near the electroweak scale, near the mass of the Higgs, and we should see it at the LHC. Tentatively, it seems that's not right either. So what is the third option? What are we left with? And the answer is we don't know. The answer is that it's easy to say, well, we need something new, right? We need a new paradigm. We need to go beyond quantum field theory and Ken Wilson and effective field theory and think outside the box. But it's hard to actually do it, right? It's hard to actually come up with a scheme that explains why the mass of the Higgs is what it is. Because effective field theory has worked so well in other contexts. You can't just say effective field theory is wrong. You need to give some principled reason for why it fails in this particular case. Now, having said that, let me be super duper honest. Let me sort of air the dirty laundry here. The Higgs mass, or the hierarchy problem, that's a problem. We have another problem that we mentioned already, the vacuum energy, okay, the cosmological constant problem. And this can be put into the language of effective field theory. The vacuum energy can be thought of as a term in the Lagrangian of the world. And that term is simply a constant with no fields in it whatsoever, okay? So that term, the vacuum energy, appears in the Lagrangian as just a number, call it rho lambda. That's what it is. And the units of rho lambda, rho stands for energy density, lambda stands for the vacuum. The units of rho lambda are energy to the fourth, better be energy to the fourth because it's the same as the Lagrange density. And therefore, you expect, or you would guess, that rho lambda should be of order the Planck mass, 10 to the 18 GeV, to the fourth. So just to get my numbers correct, that's 10 to the 27 electron volts to the fourth. But then you observe, you actually measure it, right? We have measured the vacuum energy, the cosmological constant, and what you observe is rho lambda is 10 to the minus 3 electron volts to the fourth power. So this is a little bit more sophisticated, a little bit better than what we did in the field theory lecture. In the field theory lecture, we said, look, there's an infinite contribution to the vacuum energy. We don't know what's going on with that. So on the one hand, it was a worse discrepancy. Infinity is bigger than this discrepancy. So this is where we get rho lambda observed over rho lambda theory. Let me not even call it theory. Let me be more honest and call it guess. Expectation is 10 to the minus 120, the largest discrepancy between theory and observation in all of physics. When we just did the thinking of a quantum field as a bunch of modes that were harmonic oscillators, and each of them had a vacuum energy, a 0-point energy of 1/2 h bar omega, it was an infinite difference between the classical and the quantum values. And so on the one hand, you say, well, infinity is bad. But on the other hand, you say, clearly we don't know what we're talking about, okay? Here, the numerical discrepancy is not as big. It's not infinitely big. It's only 10 to the 120. But on the other hand, we would think that we do know what we're talking about now. This is just a statement that, we don't need to know what happens at ultra-high energies to know that whatever happens, they should contribute to the low-energy cosmological constant. And they should contribute a huge amount. And they don't. And nobody knows why. As I said, it's so bad that the best theory that we have is that we live in a multiverse and there's different values of the vacuum energy in different parts of the multiverse. That's not a good theory. It's not a very quantitative predictive theory right now, but it might be right. Or it might be that there is some other dramatic deviation from the paradigm that needs to explain this. And the reason why I say I'm airing the dirty laundry is, I said that effective field theory is wonderful, it works really well, and that's true. It's been used all the time, and it's been checked, and we're definitely on firm ground. But in the known theory of physics, in the core theory, as I called it in the big picture, borrowing a phrase from Frank Wilczek, of the standard model of particle physics plus gravity, there are only two numbers that are not dimensionless. Okay, in the actual Lagrangian for the theory of physics that we know. There's a little subtlety with the QCD scale for quantum chromodynamics for the strong interactions, but that's explained. We understand that. There are two literal dimensionful quantities that appear in the physics that we know, the Higgs mass and the cosmological constant. Those are the only two. All the other parameters, like the fine structure constant, are dimensionless. And so we have two dimensionful parameters, and in both cases, the effective field theory guess or expectation is wildly wrong. We are 0 for 2. So there's many other, I got to keep emphasizing this, there's many other contexts in which effective field theory works really, really, really well. So there's good reason to think it's true. But for the case of giving us expectations for the values of dimensionful parameters, it has failed us miserably in the real world. And we don't know why. Again, it's cheap and easy to say, well, the framework is wrong. Great. Tell me what the right framework should be. You would make a lot of money, or you become a famous physicist if you could actually say, here's how we need to do better. It seems to be something where you need to actually go beyond quantum field theory. But again, that's easy to say. The energies for like the vacuum energy, the energy scale, 10 to the minus 3 electron volts is really, really low. That's lower than chemistry energies. This is in a regime where we think we understand physics pretty well and quantum field theory works pretty well. There needs to be this incredible cancellation to get rid of all the contributions from higher energy states in the calculation of the vacuum energy. So, once again, good news and bad news. Bad news is two big problems that we don't understand the resolution to in the effective field theory framework. Good news is two big problems we don't understand the resolution to. We're in this bad situation in modern physics where we don't have direct conflict between theory and experiment. What we do have are these naturalness problems, these fine-tuning problems. Right now, these problems are the best clues we have to going beyond the physics that we know and love. So it's important that we love the physics we know and love. It's also important that we keep in mind how best to go beyond.